Well, I waiting for the starting the meeting recording. Okay, I guess that we are ready. Well, I guess that you can see my presentation. I hope that you can understand my talk, because I am not employed. No, I'm not talking in Spanish, nor English, nor Portuguese, or something like. I talking in English. You know, English is ancient English. Ancient English is a non-standard dialect of English that is in constant flux. Every week there are new discoveries. For example, I have not defective verbs. I could say I will come, and it's totally right. I could pronunciate priority are the same. I could say a lot of cows instead of cattle. The words are clearly separated instead of having of mix in a mumble. There are some of the new linguistic discovery of the week, like you are sending fruit. It's like está mandando fruta. Yeah? Or I'm lonely you is something like te estoy cargando, chabón. Or she drinks me off point, me tomó de punto. Okay, good. Enough English for today. Now back to the topic. Well, the last episode will be concentrated in two main topics that is relatively the same. Is the transaction processing inside our Ethereum-like node. The transaction, we visited the transaction message in the last talk, but the transaction as the block message could be sent other peers, but notably the transaction.
No sé si es esto que...
Oh, sorry.
No, fíjate si no tenemos batería, eso.
No, cargándose. A ver, ahí.
You have the microphone open.
Ahí está, no, yo lo acabo de terminar. No, eso no.
No, pues a mí.
Okay.
Un controlador que no esté conectado a la cámara.
Que los que están haciendo problemas. Julián, silencia tu micrófono, por favor.
Es que no se escucha.
Oh.
Creo que debe ser para mí problema de...
Okay, thanks. Well, but in the case of a transaction, we have other paths. The transaction could be received from an external client, what is usually called the dApps, the distributed application, or the wallet. I don't like that denomination. It came from an external client that usually sends a JSON RPC. JSON RPC is the way that Ethereum and notably Bitcoin, also Bitcoin, have defined to connect to a node from external clients. They use them a JSON file using different transport. It could be HTTP, HTTPS, or you can use WebSocket, and then the node receive the JSON RPC message, react with an answer that is also in JSON RPC format. For that, we internally have implemented what is called internally the Web3 is not really a good name. It was called Web3 maybe 4 years ago because the popularity of one of the client libraries, the Web3 JavaScript and Web3 in other implementation like in Java and in .NET. But Web3 is something that is related to the client library. Internally, we are using JSON RPC, but in the code, let me show some of the code. In the code we have a WIP3. I will switch to a better presentation. Oh, sorry. I guess that is better to go to distraction free. Yes. And then this is the Web3 defined in our code. Notably, is an interface that is implemented in other codes. We started this code 4 years ago. Maybe it's a bit long with many responsibilities. It was improved along the years. For example, now it's just 10 different sub-interface. You can see here that we have now different modules related with subsets of the external interface with the Web3 and JSON RPC clients. But still, I guess that is has many responsibility. Maybe we need to sometimes we need to refactor this to have helpers instead of implementing in this interface all the modules. But for example, let's go to see some short module, maybe the Web3 debug module. Web3 debug module is short. It exposes some methods that correspond exactly with the name of the method that came in one of the fields in the JSON RPC request. JSON RPC request has a field, predetermined, a pre-established field that describes the method to call. And the method to call is the debug trace transaction. For example, this is the way the module connect the external request with the internal implementation. This map is made, is executed internal code that is near our Netty Netty extensions. You remember Netty is the library what we are using for TCP and UDP communication. And also we are using Netty for HTTP, HTTPS, and I guess now we are using for WebSocket communication. And then you can extend Netty to say, okay, if this post has a JSON RPC message, read the JSON RPC field and map and call this internal method. Usually, this module, if you want to extend this module, you need only to implement this module. Internally, usually they derive all the implementation to other module that has not, that is more separated in terms of naming of method, that this one that has to be the same method that came in the JSON RPC message. For example, there is a debug module that is the real implementation, and this debug module usually has only one implementation. Sorry, I don't remember here. And then this is the implementation of this short module, but there are many modules, and some ones are very, very long with many responsibilities. Usually, this module implementation are injected at the constructor level with many helpers. For example, in this case, the block store is in charge of retrieving blocks from our database. Receive store is in charge of retrieving transaction receive data, and so on. This is maybe this is a bit complicated. Not in this case, you have only 4 arguments in the constructor, but sometimes you have. I'm not exaggerating, but I remember that we have maybe 10, 15, or 20 constructor parameters in some cases. It's a bit messy to me. We need to improve this code. Okay, back to the presentation. When the transaction is received, I guess that is in one module that is called the ETH module. But the transaction is received in a format that is called the raw transaction usually. What is a raw transaction? The raw transaction is only a byte hexadecimal string field that contains the serialization of the original transaction with the signature added. That is the complicated part from the code at the external client. You must know how to serialize a transaction, how to sign the transaction, and how to send the hexadecimal result. That is maybe is the only use case that adds complexity or to the external client, how to sign a transaction. We respect the transaction format from all the Ethereum ecosystem, as far as I know. So we cannot need to change the wallet. That is a good point for our node. We don't need to change the wallets and external client to conform to a special format in our node. No, we respect until now, unless the Ethereum format. There are other blockchains that are forked from Ethereum that change that format, and they are forced to use different new wallets and new libraries, but is not our case yet. Okay, and the other path to receive a transaction is from other peers. You know, from the last talk, I guess, a node could have many peers, and the peers could be discovered from the bootstrap nodes. Then the peer could send a transaction that he also received. Usually, a node doesn't send to our node a transaction before the transaction was validated by the sending node. You cannot spam the network with that invalid transaction. The transaction that you receive should be validated by either peer. But because a peer could be a bad peer or a malign peer implementation, we must to control, to validate the incoming transaction. The transaction message comes in a encoded format. We discussed the encoding LP, I guess that in the first talk. Then come into the message queue. We discussed it in the last talk. Came to the message handler that has a thread that are consuming one by one the incoming message. We are discussing internally to have many consumers instead of only one, and to have different message queue for different kind of message. For example, we could have a message queue dedicated to blogs, a message queue dedicated to transaction, a message queue dedicated to other kind of message. But now we have only one message handler, only one message queue. The message handler gives the transaction message to what is called the message visitor. We discussed it in the last talk. And the message visitor, depending on the kind of on the incoming message, send the message to different code segment. In this case, there is a new thing that is called now the transaction gateway. What is the transaction gateway in our implementation? Let me go to transaction, oh, sorry. Gateway, yes, here. Well, it's something that was called recently, some months ago, has some helpers. Notably, it has a channel manager helper. I guess that I mentioned the channel manager in the last talk. The channel manager has an internal list of all the peers that are now connected to our node. Why the channel manager is here? Because in some use cases, the transaction gateway should send resend the received transaction message to other peers. I will show the code. The other helper that could be interesting now is the transaction pool. I mentioned the transaction pool in the last talk again. The transaction pool has the responsibility to keep a list or a set, could we say, a set of transactions that are known by our node, but are not yet included in a valid block. It's called also transaction pool in the Ethereum ecosystem, and there are in the Ethereum ecosystem there are utilities like the EtherScan web page that shows the transaction pool that is active. The transaction pool is not unique. It depends of each node. Some node could have maybe 100 pending transaction. Another node maybe has another transaction and not exactly the same set. It's something that could change from node to node. But that is maybe the main thing to take into account in the next discussion. The transaction gateway then has a method to receive a pre-processed list of transactions from the message visitor. Notably, one of the things that this code do is to record in an internal memory list that this transaction was included in that is known by the sender node. In this way, we say okay, that the peer node from Alice already know this transaction, so we don't need to relay this transaction to the Alice node. We need to relay to the other nodes. There are many. There are similar code for keep the list of peers that know some block also. So we don't rely a block or a transaction to a peer that we already know that knows that information. And the second thing that this receive transaction from method do is to add the transaction to the pool. Notably, it can add many transactions. This code is relatively important in our implementation. We could visit the code. This is an interface. I go to the only one implementation. I could discuss this implementation or the current code because notably you see that the add transaction receives a list of transactions, but also returns a list of transactions. Why? Why it is prepared to return a list of transactions? Well, You in the transaction message could have many transactions. I didn't mention that. But when the transaction came to our node, we need to check the valid state of those transactions. So you can receive maybe 2 transactions, but maybe only one is valid for our node. So this is the responsibility of this code. It validates the transaction. For example, now is checking if the transaction is already added to the internal list. I know that Mr. Len just wrote a code that I guess that it was mentioned yesterday that improved this the detection. And then when one of the thing to do is to check if other transactions are not valid. It's a domino effect. I will discuss this in a coming slide. But sometimes you receive a transaction, then this transaction is valid, and also there are pending transactions that started to be valid after this one. Why? Remember, when we discussed it in the first talk, the account state has the balance of the account and has another field that is the knowns. The knowns is the number of transactions that account already sent. Well, the knowns started with 0. The transaction that we received, maybe the pool has transactions that are too much advanced to the current account state. I will discuss this graphically in a coming slide. But this is the reason for this code. This code tries to determine if the incoming transaction, the new transaction that now we are started to know, have another pending transaction that started to be valid. So is what is called the successor transaction. And then for each of the other transactions, this code dispatch an event about their new pending transaction received and the transaction pool change. And then return the other transaction. So if we return to the code that called this method, here, you notice that we don't use the return list. Well, we could discuss if this is the best way, because now the transaction gateway could receive the other transactions, and then it could decide to rely in this moment to relay the other transaction to the other node. But it's not the case now. Some months ago, we have code here to relay the other transaction now, but it's not the case now. The current implementation take advantage or take into account the events that the transaction pool emits. So when the transaction pool emits that there is a new pending transaction, the transaction gateway receives the event, and then he determines what set of nodes already know that transaction, which set of nodes don't know the transaction, and then for each of the new nodes, send the transaction to relay the transaction using the channel manager. Broadcast the transaction using the channel manager. You can ask why. If we determine the node to skip, and then the broadcast transaction receive the node to skip. Notably, we don't send the nodes to receive the transaction. We inform to the channel manager the nodes to skip, and the channel manager knows the rest of the nodes. The channel manager is a dynamic, it has a dynamic information. We don't keep which are the nodes now. Is the responsibility of the channel manager. But the channel manager is returns the set of nodes that receive the transaction, and then we record that transaction now is apparently known by that peer. That is the sense of this, the meaning of this code. Maybe in my personal opinion, I guess that it's better to relay the transaction when the transaction pool decide that are new transactions that are valid. Why I think that? Because this event, the transaction, a new transaction, a pending transaction could be in the pool, could be generated in many ways, not only by an incoming transaction. It could be generated by an incoming block, or because there are incoming blocks that change to alternative change, and then the discarded block should the transaction included in the discarded block should be added to the transaction pool, and then it could generate. I don't know if this is the case now, but sometimes we could generate a new event. It's not the case to relay again the transaction. But we need to discuss this in other time, maybe with boxing gloves. Oh, yes. The transaction pool could receive new transactions from the JSON RPC or from a transaction message, and then it could receive also incoming block. Why? Because when the incoming block reach our node, the node say, oh, there are new transactions included in that block. Then I should remove the transaction, those transactions from the transaction pool. Also, maybe this is the main case to have a transaction pool. The transaction pool is useful in the miner nodes. We discussed the last talk about the mining process, and the mining process acts to the transaction pool. Give me a set of transactions that are now valid, and I could apply in the next block, and then the next block could be built by the miner server. Maybe it's the main use case to have a transaction pool. The other use case to have a transaction pool is because we have external methods that came from JSON RPC that an external client could ask our node, give me the list of transactions you already know, but are still not included in any valid block, or less in any block in the main blockchain. That is part of the protocol that every Ethereum client should comply. There are methods for external client using JSON RPC to ask the node, give me the list of transaction pool. Maybe you already know the Explorer is. Yes, I guess it's the Explorer. The Explorer shows the transaction in pool. I know this is 5 transactions in pool. I guess that you can see the message at the middle of the screen. That is not the transaction in the pool in the network. It's the transaction in the pool that are inside the node that this Explorer is using now. The Explorer is connected to one peer, and that peer has a unique, maybe a unique transaction pool that is his partial view of the rest of the network. There is no such thing like a transaction pool for all the network. Transaction pool lives inside each node. And then maybe this is why to have a transaction pool if you are not a minor node, or if you are not a node that exposes this information using JSON RPC. Well, the other reason is if you receive a transaction, you must validate the transaction, even if there are other transactions pending. That is maybe the other use case for a transaction pool. We cannot remove the transaction pool for nodes that are not miners or are not exposed the internal information using JSON RPC. It's essential to the node to validate the incoming transaction, to know what other transactions are now. Why? Well, because the transactions, I mentioned that each account has an address, or we can say the address is the account A or the account B, but it also has a balance, but also has a field that is called nonce. The nonce in the account A in this slide is 20. Then the 20 indicates that these accounts already sent 20 transactions from the transaction with nonce 0 to the transaction with number 19. Then the only next transaction that could be executed and included in a block from this sender, the account A, is the transaction with sender A, but with nonce 20. We cannot process other transaction. But if we have in the transaction pool 3 transactions with the nonce 20, 21, and 22, well, all are valid, because the miner algorithm could choose to execute the 3 transactions one after another. But it should be executed in order. We cannot include the transaction 21 before the transaction 20. We need to, the block to be valid should include transactions that are directly connected with the account state. If the current account state say the account A has announced 20, the only next transaction that could be included directly is the 20, but if there are other transactions with consecutive nonce, they could be included also. But sometimes you receive a transaction with nonce 24, maybe, because the network, you can send many transactions, and maybe some transactions are received in your node before other transactions. Is non-deterministic. And so these other transactions that are not directly connected in a chain to the account state, internally I guess that is something that it was invented by the Golang implementation Get. It's called the Q transaction. Q transactions are the transactions that we know, but are not directly connected and cannot be processed until we receive the transaction with nonce, in this case, 23. Without the transaction with nonce 23, we cannot process and include the 24 transaction. So that is the reason I say that when the 23 transaction came from other node, maybe there is a domino effect. We must relay the new transaction 23 to other nodes, and we must relay the QA transaction that is the 24. Our algorithm and the Ethereum client algorithm doesn't relay a transaction that is Q. only relay the transactions that are pending in some way connected with the current account state, unless for the account state that this node knows, because every node could have different blockchains at some moment in the time. That is the discussion to have two different transactions, a kind of transaction inside the transaction pool. There are JSON RPC method that asks to the node, give me the pending transaction, give me the queue transaction, or give me all the transactions. There are methods that was invented by the Golang implementation, and then they were adopted by other implementation, and now we have some, I guess that 1 year ago we added those concepts to our internal implementation. Sometimes we have a problem with this. There is an issue reported by Pulice Donato some weeks ago about their organization blockchain maybe could break the internal transaction pool. It's not, I'm not sure that is the case, but there are some pull requests to improve the behavior of this transaction pool when the blockchain has fork, alternative change in the middle of the time. Okay. Well, I discussed that the transaction relay occurs when the transaction pool emits an event and the transaction gateway receives the event and then relay the transaction to the node that the channel manager knows, but the transaction gateway is sure that those nodes don't know this transaction. Okay. Maybe this is a bit convoluted code that we have. Is part of our code, is part of the heavy inheritance from the Ethereum Shape project, but the transaction execution is a bit long, unless, to my opinion, it should be refactored and simplified. But well, we could discuss that. But the main thing to see in our node that usually you don't execute a transaction alone. Some years ago we executed the transaction in the transaction pool validation process, but it was a very heavy process. We could receive a lot of transactions for other nodes. Then we usually execute the transaction only in the miner when the new block is built, or only when we receive a block from other peer or miner. That code is called block executor. I guess that block executor could be simplified now because it has missed use case that maybe should be refactored to be clearly separated. But the main thing that the block executor has helpers, like notably the activation config. This is something that appeared some years ago. Maybe I discussed it in the last talk, but the activation config has information about what hard fork should be applied at this block height. You know that we apply different hard forks in our mainnet. Maybe we change some consensus algorithm, or maybe we change the internal format of the block or something alike. Then the activation config has the needed information to determine this block is valid because we are at the high 1 million, but maybe it's invalid if we are at the high, I don't know, 800,000. And the other thing that is important, unless in our implementation, is the repository locator. Repository locator give me the view of the world state, all the accounts and storage of the contract at that block. So if I receive the block 100, the repository locator is in charge to retrieve the world state corresponding to the parent block. Then, starting with this world view, we can execute the new block that just arrived. And so on. Then this is a glimpse that we have more than one use case in this, more than one responsibility maybe in this code. This execute and fill usually execute the block and fill some missing piece of the block because we are mining a block. We are building a new block, and then we need to execute and put some of the result into the block header. For example, the world state hash root. But sometimes we need not all this fill logic. Sometimes we need only to execute and validate the external block. It's different. We could discuss if we could maybe in the future separate this responsibility more clearly. Well, the validation of the block has many steps, but then when the block is validated, there is an internal execute. Sorry, I don't find, yes, an internal execute that that is in charge of this logic to iterate of each of the transactions that the block has. This is the code that really execute after the initial validation of the block, that the transactions are valid and apply the transaction world state changes. We don't have exactly a clear path to execute a transaction. We have here, for example, a transaction executor factory that creates a new instance of what is called a transaction executor. Then we have here 9 constructor arguments to the transaction factory. The transaction executor is one of the important code that we need to understand, but we are now under the process of refactoring the transaction executor, because the transaction executor, I'm now in a branch where that refactor was applied, but maybe I don't remember now the state of the public release. But the executor was refactored recently to be simplified, but it still is a bit of mess code. Look at all the internal state that has the many things that it managed. Internally, they have many methods that are invoked. If you have a recently branch before this refactor, you must call these 4 methods from your external code. You need to call the init method, call the execute method, call the go method, and call the finalization method. Now we are refactoring all this in only one transaction. But each of these methods is still a bit long and has many responsibilities that we should review in some time in the future. This is maybe all this code. Sometimes we discover bugs. The security guys discovered recently a bug some month ago about the gas, the gas limit and the gas process. There are many logic decisions that execute the code in a slightly different way for precompiled contracts than from the contracts that are included maybe in compiled Solidity. We need to improve this code. It's a bit long. Each of these, the method, for example, I guess I don't remember now, but the execute method, the execute method that I started, the next week I could reach the start of the method. Well, this is the execution of the transaction. But if the transaction is a precompiled contract, it's executed here in this method. But if the transaction is a call, an invocation of a compiled contract, it's executed in other different methods. It's a bit strange. And we have some problems and some bugs in this code because this is part of the original code of the Ethereum shell implementation. Well, back to the slide. The transaction executor have another factory, the program invoke factory, and then the program invoke. What is the responsibility of those? Program invoke factory. The program invoke factory creates what is called the program invoke, and the program invoke is has a view of what is the current world state executing this transaction. For example, what is the balance of the current sender? What is the sender, the origin address? What is the gas price of the current, the minimal gas price of the current block? With the previous cache of the parent block, which is the address of the get coinbase is the address of the miner of this block, the timestamp of the block. It has a lot of information that is used, by the execution of a compiled contract or precompiled contract. For example, the implementation here is program invoke implementation that has a lot of state, and notably it has a lot of constructor arguments. We should maybe refactor this one to have less scattered state. We have more than one way of create this code. Well, it's a lot of code that we need to rank. And then at the end, we have the program. The program class receive all this data and then is in charge of not exactly executing the code of the compiled contract if there is a contract. Not only the Ethereum shell people split the responsibilities between the program that has the stack of the virtual Ethereum, the virtual machine, the memory of the transient memory of the virtual machine, and the storage of the current contract from the contract execution. But we have many of state. It's a long code that should be reviewed, and sometimes we have problems here because we discover some bugs along the years. But that is one of the things to review of our code. And the other one is the VM. VM is the class that really executes the opcodes in the compiled contract. Sorry, I don't explain now all the opcode because we recorded a dedicated talk about the Ethereum virtual machine. Maybe we could record again or give that talk again in English, unless or if someone could give it in English better. But there is a recorded talk about the Ethereum virtual machine. That is in our implementation. We try to be comply with the Ethereum virtual machine. And then this is a code that internally receive a byte array with the opcode to execute. Sorry, you can read that this a very long code, but I don't remember now. The maybe it's here. Well, I don't remember exactly now the method that involved the code, but I can show you one thing. For example, there is the used gas. Sorry, then is in the program. In the program, we have used gas. Sorry, I don't find now the internal code, but recently it was refactored to control better the code of the gas that is consumed in each opcode. Because some months ago we discovered a bug in our implementation that allows the bad people, I don't remember, malign people, bad people to increase their balance, account balance, without having funds, because the gas, some of these variables has an overflow in an addition operation, and then the balance comes to be negative in Java, but in some code is taken as a positive balance and could be added to the final account without having the funds. It was called the Bahamas bug. It was fixed some releases ago, but part of the problem is that this is a very long code. The VM and the program code is very long, maybe it's a bit messy, and we have all other issues in the past. For example, implementing a new opcode, which part of the code we need to change, if we need to add a new opcode, a new gas, consumer gas for this opcode, and so on. Internally, you can see the execution of all this in internal method of the VM implementation. Do address is the code that is internally called when an opcode address is detected in the bytecodes. Internally, the VM has a big switch, sorry, here, that is the execute opcode, that now we need to know the activations of the hard fork depending on the current block height, then switch for the new operation code. Notably, the operation code is not coming as an argument. It's part of the internal state, so maybe it could be changed in any other place, and we have trouble. And then each of the opcode is executed calling one of these methods. Maybe this method should be final, because in this way to determine the method to call. You know that in Java, all the methods are virtual. The Java compiler doesn't know at compiling time what method to call exactly. It's determined at runtime. Maybe we should improve this, changing this method to final, so nobody could redefine this method in subclasses, and then the compiler could have better information to determine at compile time which method to use. This imposes to our implementation a performance issue, because the call of each of these methods could be improved. Well, and there is not so long. It's long only because there are many opcodes, but usually the opcodes are simple, are short. That is good, but sometimes we have, I don't know, do call. To call that is called another contract is a lot of code to determine which gas to pass to the other contract, how to receive the code to other contract, and then after all this logic and the compute of the gas, this is new code where the gas is not adding the gas only with Java arithmetic operation. We have now a gas cost helper that add the gas checking for overflow. The gas is alone in our implementation, but now security team added code to check for the overflow of this operation. Well, and after all this code, it makes a new message call that sends a lot of data to the new contract. Call to address is part of this implementation, and the call to address call the program has code to call a precompiled address or a contract, and the program has call to address that, let's go to see a bit this code. Call to address again has a lot of logic to implement a simple call invocation to other contract. It's really a bit difficult. Recently, we added some information to the execution of a transaction that is called the trace of a transaction. And it was a bit difficult because we need to change many of these long code. This is one of the new lines we added, but we need to add it because this code has many paths and many different use cases. We should add this new feature with very careful. We should add this new feature, changing many of these internal classes. Maybe this is the code that could hurt us in the future, because this is important for consensus. If we have an uncovered bug here, maybe it could be a hard bug, as the Bahamas bug. In my personal position is we should rewrite all this code. It cannot be refactored, but it's a personal position, and you can come to meet me with boxing gloves, and we can discuss in other time. Okay, that is enough for today. Any question?
No. Thank you, Angel.
Thank you.
Well, now everyone now I guess that everyone could add code to our core project. That is this is the basis for a training material for the new core team, I guess. But I want to share all this in a more open position to all the developers in the company. To me, this project is important because it's the basis for many of other projects. I think maybe of you know my position that we should improve this code. Maybe we could in the future we could switch to other implementation directly, maybe to a Java implementation, a Go implementation, or a Rust implementation. But now we don't have enough time maybe to do that, and so some labs should be put over this code. Well, thanks to all. I will stop the recording.
Thanks, Angel.